Hi everyone, my name is Ayman Izzuddin and I'll be joined by Mohammed Al-Makki to talk about Autophase V2 towards function level phase ordering optimization. This work was supervised by Dr. Gini, Dr. Amir, and Dr. Chris. In this work, we present a new approach to tackle the phase ordering problem. Industrial compilers use many optimization methods to optimize a program. The phase ordering problem is a problem of finding a sequence of optimization passes for a given program such that the output is optimal according to some performance metric, such as code size or runtime. The current solution in modern compilers uses hard-coded expert-picked optimization sequences. These sequences are engineered to optimize for a specific optimization metric. For example, the OZ sequence optimizes for code size. This solution is far from optimal, as has been shown by research, and can be outperformed by tailoring the phase ordering decisions to individual programs. To illustrate why this is a problem, let's first take an example program and perform two optimizations on it: constant propagation and simplified CFD. In the example, x is a variable initialized to 10 and never changes, and so its value is constant. The condition branching, therefore, is always going to take the first branch. Applying simplified CFD followed by constant propagation results in the code below. However, the output is not optimal. Instead, let's change the order of passes. Applying constant propagation first, then simplified CFD results in an optimal program. This shows how the order of passes affects the final output. Even more, there is a huge amount of possible orderings, which makes enumerating the complete search space practically impossible. In fact, the phase ordering problem is known to be an NP-hard problem. To introduce our work, let's first discuss some aspects of the LLVM project. The LLVM project is a set of modular and reusable tools and libraries for compiler tasks. LLVM project includes different tools such as the op tool, which performs optimizations, and Clang, which is a fully fledged C, C++, and Objective-C compiler built on LLVM. Compilers usually represent a program in an intermediate representation. LLVM utilizes a platform-independent representation called the LLVM IR. The LLVM tools for compilation are divided into three pluggable components: frontend, optimizer, and backend. The LLVM frontend is responsible for transforming the source language into LLVM IR. The optimizer performs a variety of analyses and transformations to improve the target program performance, such as running time or code size. It also includes a predefined and hard-coded sequences of passes that are known to improve some performance metrics in many cases. The backend then transforms the resulting intermediate language into the target instruction set. LLVM IR is a low-level RISC-like virtual instruction set. It resembles the assembly language in many ways. It is composed of nested elements, the root of which is a module, which is the compilation unit. Each module consists of several functions and other elements. Functions are further broken down into basic blocks, which are sequential groups of instructions that ends with a jump instruction. The optimizer defines different types of passes depending on which part of the program the pass runs on. Module passes run on the whole module and may, for example, delete functions or perform inlining. Function passes run on a specific function. Other types of passes include CFD and loop passes. Solutions to the phase ordering problem has focused so far on applying a single optimization sequence to the whole module. The single sequence is applied to every function in the module. However, these functions can have vastly different properties and characteristics, making it benefit from different sequences. Thus, we propose a new approach by tailoring the phase ordering decisions to each function within the module. To motivate this new approach, we performed exhaustive search on a single module with 5 functions and using 13 function passes with an optimization sequence of length 5. The search was carried on the module level and function level. As you can see from the table, the results show that different functions benefit from different optimization sequences. Furthermore, some functions benefit from the same set of optimizations but in different order. The function-specific phase ordering were able to achieve 2% code size reduction improvement over the module level 1.
Hi everyone, I am Mohammed Al-Makki. I will continue the presentation and show you our experimental setup and results. First, let's have a brief introduction to reinforcement learning. In reinforcement learning, we have two characters, the agent and the environment. The agent interacts with the environment by observing its state, then based on this state, it will decide to choose an action to take. After applying the action, the state of the environment will change and a new reward will be calculated. The goal of the agent is to maximize the cumulative reward. The reward is a numerical value that measures how good or bad the current state of the environment. Here in this diagram, we can see the agent-environment loop interaction. The agent takes an action and receives a new state and reward. Now we introduce comparison. To implement our function level phase ordering environment, we use the comparison framework. The framework is a set of reinforcement learning environment for compiler tasks. We implement our function level phase ordering environment by extending the LLVM phase ordering environment comparison, which currently support only the module level phase ordering method. In this diagram, I'll show you the function level phase ordering environment workflow. First, we split the LLVM IR module into multiple functions. Then we add one function to the environment. In the environment observation in the Autophase feature vector, we use the feature extractor to compute the feature vector. Next, we feed the feature vector into our agent, which is a deep neural network. After that, the agent will choose an action. In this case, our action is the function optimization path. Next, the function optimization path will be applied to the function and the reward will be calculated. So with this workflow, the loop will continue until a fixed number of steps, and then the next function will be loaded in the environment. To demonstrate the effectiveness of our function level phase ordering method compared to the module level phase ordering method, we performed random search experiment. The random search experiments have two parameters, the search time and patient. The random search operates by selecting passes randomly until a fixed number of steps have been evaluated without improvement in the reward. After that, the search will terminate and search for a new path sequence. This fixed number of steps without an improvement is called the search patient. Also, the search time is the amount of time spent searching for the optimal phase ordering for a module or a function. In this table, we can see the results of the random search experiment on 15 benchmarks from the cBench dataset. The table states the method, the search patient, search time, and geometric code size reduction compared to the OZ flag of the 15 benchmark for 3 experiments. As we can see in the table that using the same search time of 2 minutes, our method was able to achieve nearly 4% improvement over the module level method. Also, it was able to achieve nearly 9% improvement over the OZ flag. In addition, we can increase the search time for the module. In addition, when we increase the search time of the module level experiment to 1 hour, our method was able to achieve nearly 2.3% improvement over the module level method. This shows that our method was able to achieve better code size reduction than module level using just a cheap search time budget. In this figure, we can see the code size reduction compared to OZ in the 15 benchmark of the 3 experiments mentioned in the previous table. We can see in 13 benchmark, our method was able to achieve better or similar performance to the module level method. Also, we can notice that in the CHA benchmark, our method was able to achieve nearly 60% improvement over the OZ flag. Now let's go to the reinforcement learning experiment. To run our reinforcement learning experiment, we use RLib framework. Also, we choose BBO with the default configuration as our learning algorithm. In this table, we can see the results of the reinforcement learning experiment the result of 2 reinforcement learning experiments on 2 datasets, the cBench and CHSON datasets. In both experiments, we set the episode length to 4 to 5 and the number of episodes to 50,000. In the training cycle over the function of the benchmark in the dataset, and testing is done by running out the agent using the same 45 episode length. As you can see from the result, that we will able to achieve 1.5% improvement over 1.5% improvement on C-bench dataset and 9% improvement in CH stone dataset over the OZ flag. To test the generalization of our reinforcement learning algorithm, we trained on Anka bench dataset, which is a dataset of millions of modules. In testing, we tested the agent on 3 unseen datasets: C-bench, C-smith, and CH-stone datasets. We run the experiment for 100,000 episodes using episode length of 45. In this table, we can see the results of our reinforcement learning generalization and experiment on Anchorage. We can see that we achieved 6.4 improvement over OZ on CH stone dataset. Also, we were able to achieve near performance to OZ flag on C-bench dataset, but we get worse performance than OZ dataset on C-smith dataset. So in general, we can see that from this result that our method has a potential for generalizing over unseen datasets. So in summary, in the random search experiment, we were able to achieve nearly 9% improvement over the Z flag. And also, we were able to achieve nearly 2.3% improvement over the module level method over the module level method. This experiment was done on the C-bench dataset. Also, in the reinforcement learning experiment, we were able to achieve 9% improvement on CH stone dataset and 1.5% improvement on C-bench dataset over the OD flag. Finally, I'm going to talk about feature role. First, we think designing better feature structures that are suitable for function will help in improving the performance of our method. Next, we think that training on large representative dataset will help in improving the generalization of the agent. In addition, doing more analysis for the buses and their interdependencies will help in designing more efficient solutions. Also, in our experiment, we omit the module passes. We think that a better approach will combine both the function level method and the module level method. Finally, exploring different machine learning approach may result in finding a better machine learning approach than the reinforcement learning approach. So we reached the end. Thank you for watching.